Um, Welcome everybody. I'm Brandon Davies, so I'm going to be presenting for the next 5 days, and um, the topic for the first 4 days is going to be transmission line protection. So try to break the topic up into some kind of basics about transmission lines, and then dive into some of the protection schemes and things like that in the next few classes. And then I'll wrap it up with one class on bus protection as well. So. Um, just quick agenda for today. We'll start out with some introductions from everybody. I'll give a little bit of background on myself. We're going to look at transmission lines as part of the power system. We'll take a look at the physical characteristics and electrical characteristics. Both are important to know about as a protection engineer because you got to know where your failure modes are, and how the electrical system is going to respond to those different failure modes. We will take a look at some various fault considerations, what types of faults you need to look out for, how the system's going to respond to those faults. And then we'll start at the end of the class. I don't know why that transitioned on me there. We have some timers on here. But anyway, we'll at the end of the class, we'll start talking a little bit about protection systems and the objectives and some of the fundamentals about line protection itself. So we'll start off with introductions. I'll go first, and then we can go around the group on the call here. I'm excited to get to know all of you, and I want to keep this as interactive as possible. So I've got a few places in here where I've got some questions, kind of roundtable, get your ideas on things as we go. But if at any point throughout any of this you get a question, you want me to elaborate on something, you're confused about something I'm talking about, let me know, speak up. I'll try to watch the Teams chat here. If you want to put your hand up or something, you can, but just flag me down. I'll do my best to, fill in any gaps on there. So a little bit about myself. I have been in the industry for just about 19 years. I graduated from the EET program up at UMaine in 2006. 2011, I got my professional engineer's license. Then I ended up finishing a graduate program, an online graduate program from Michigan Technological University in electrical engineering with power focus a few years later. It was pretty good experience, and TRC paid for the whole thing, which was an added benefit. As far as my work and career experience, I started at TRC right out of UMaine. Got hired right out of graduating there as a protection and control engineer. I eventually kind of worked my way up through a whole variety of different positions, but generally working within the protection space or system protection relay settings type space. Through various leadership roles, up the supervisor, manager, and then director of our national system protection and automation practice. I'm currently in a role as our chief technical officer for our substation engineering group, which is about 300 to 400 people, roughly. I do a lot of our technical stuff, digitization efforts, lead a whole variety of stuff for our team on the technical side of things. As far as some other industry involvement stuff, I'm pretty active in the IEEE PES Power System Relay and Control Committee. A member of both the Substation Protection Subcommittee and the Main Committee. I'm actually currently the chair of the Substation Protection Subcommittee as well. So that group does a lot of the industry publications and standards related to protection. So you get to learn a lot of really interesting stuff there. And it's a committee and group that collaborates to write new standards, update existing standards, write technical papers about things of interest to the industry. So I've been involved with that for quite a few years now, and I've gotten a lot out of it. So that's kind of me in a nutshell there. Again, I don't know why my slides keep moving here. but I guess they're on timing from last year. So quickly, if we can just go around the room here, I'd love to get to know each of you a little bit as well, and at least get an idea of what you're interested in, and if you've got career lined up and kind of what you're going to be working in. I'd love to hear about that as well, or just in general what you're interested in as well. So we'll go around here across the top here. Jeremy, you want to start?
Sure. My name's Jeremy Yaley. I'm in the graduate program right now, and I'm a SCADA engineer at Versant Power. I've only been doing that for the last year and a few months, so still relatively new, but yeah.
Awesome. Excellent. Kia?
Yeah. I'm production engineer, and I was working with the oil and gas project in Fort McMurray, Alberta in Canada. And that's all. I'm familiar with the mostly mechanical and basic electrical engineering.
Yeah, great. Eugene?
Hi, I'm in the graduate program as well, and then I'm working at RLC in transmission planning group.
Oh, excellent. Rob?
Hi, so I'm in the graduate program. I'm currently a program manager at the Advanced Structure and Composites Center. I run DoD applications, kind of integrating ML and AI into manufacturing practices. I have experience in nuclear power. I was on 10 years on submarines doing that. So.
Oh, cool. Awesome. Well, thanks. Nate?
Hey, I'm Nate Holliday. I'm my last semester of school here at UMaine doing electrical engineering technology. And my last few summers I've been interning at TRC. So I think we've met before, Brandon.
We have met
Augusta office.
Good to see a familiar face.
Yeah, good to see you too. And I started full-time in May as an automation engineer. So
excellent.
To it.
Yeah, we'll see each other again. And Shane?
Yeah.
Hey, can you hear me?
I can.
Awesome. Yeah, Shane Bryant. Right now I'm a design engineer at ECI, working in the protection controls. So I'm excited to learn about line protection, get into some O circles, some material I haven't really dove into yet. So it'll be good to
great. Well, I'm glad to see we've got some really great representation from a kind of a broad range of places and things like that. So I think with that we can probably dive into the fun stuff here. So I did want to do just a quick brief overview of TRC. I think probably a lot of folks in Maine know who TRC is because we've got a couple big offices here, and in general this industry is kind of a everybody knows everybody else kind of place in Maine. So we'll get to know each other over time, I'm sure, if you stick around in Maine. It's a small world. So TRC is a kind of national and slowly growing into international consulting company. We do power systems work, kind of every aspect of the power system, from the substation protection stuff that we do to renewables to system studies, distribution, transmission, kind of you name it. If a utility needs it, chances are we've got a group who does it. We got about 8,000 employees across the company. 150 office locations. So we've got offices in here in Maine, in Augusta and Portland. We've got a couple other miscellaneous ones that are part of the other sectors, or environmental sector or infrastructure sectors, but we don't have a ton of overlap with their work. So in general, we got a lot going on, a lot of interesting stuff at our company, and so I'm sure if you stick around Maine, like I said, our paths will cross at some point. So I guess starting the discussion about transmission lines, the first thing, I kind of want to start at the very basics. Obviously, everybody here has had some power background in classes, but I think it's kind of important to frame any protection discussion around the equipment that you're trying to protect. So we're going to talk a little bit about characteristics about AC transmission lines, and then what makes up the transmission system, both physically and electrically. So typically when we're talking about AC transmission, we're talking about three-phase AC systems. Generally, it's ranging from about 69 kV up to 765 kV. Internationally, there are some higher voltages out there. There's some utilities that operate their sub-transmission system, maybe 34 kV to 69 kV range, very much like the transmission system. But generally, when you're talking about the bulk power transmission system, you're talking 100 kV and above is really what we're talking about, and that's the bulk electric system by the NERC definition. So our transmission lines can be either overhead or underground. By far, the most you see is overhead lines on transmission structures, like the one in the picture there. But you can have underground cables as well, underwater cables, things like that. It's just a different construction of the line. Those generally come at a much higher cost, which is why we have things overhead more often than not. So your transmission lines, generally, they'll terminate at substations or switching stations. On kind of the end of the line is delineated by the breaker, the circuit breaker or switching device at the substation that would disconnect or connect the line to the system. So generally, when we're talking about the physical line itself, that's what we're talking about. When we start talking about protection, we'll define the boundaries with CTs rather than the physical equipment, primary equipment. But the primary goal of a transmission line is to transmit power between substations or between generation stations and a utility substation. So we need to get the bulk power flow from where we're generating power to the larger load centers, and that's what we're doing with the transmission system. So kind of overall, very simplified version of the transmission system here. We've got a variety of generators over here, those step up through transformers that apparently aren't shown on this graphic. And then we move power from the generating areas to industrial customers that might be connecting in at transmission voltages. They have their own transformers and things like that to connect into, kind of step down to their operating voltages. Or we'll go to electrical substations and step down from the higher voltage, 115, 345 kV, down to a lower voltage to connect into the sub-transmission system or distribution system, to then kind of radially feed all the other loads of the system. So, houses, businesses, factories, kind of everything that has electricity is kind of on this model. But this is a wide simplification of what we're really talking about when we are talking about the transmission system, because it's not just a single transmission line or a few transmission lines that directly connect up from a generator to the substation that feeds your town. We're talking about a very wide interconnected grid of dozens or hundreds of transmission lines that make up the power system. So this is a kind of zoomed out view of a portion of the New England grid that in Aspen, and every one of the lines in here represents a transmission line. So generally I believe the kind of pink color here is 345 kV transmission system. Red is the 115 kV, and then blue is stepping down to the sub-transmission system. So you can see, just kind of very broad level looking at this picture, it's a very complicated and interconnected system that makes up the overall transmission grid. But largely, what's connecting every bit of that together are our transmission lines. So transmission lines are constructed with a few main components. You're going to have a transmission structure. And this is generally, I'm going to be focused on overhead lines because almost all of what's out there. There are some underground stuff, but generally we're going to talk about the overhead components. And those are going to have a transmission structure. So that's basically something that keeps the energized conductors off the ground, away from things, and isolated from each other. To connect the conductors to the transmission structure, we've got insulators. So we'll have insulators, and the size of the insulator stack will depend on your voltage rating of the line. And then you're going to have conductors, and you're going to have both phase and ground conductors. So you'll have 3 conductors for your 3-phase system, and then you'll have 1 or 2 ground wires that will connect the structures together and provide a ground path for your fault current and for grounding your system and keeping it on a consistent ground reference. So the process of engineering a transmission line is it's its own very complicated process. There's a lot of very detailed and complex softwares that are used for transmission line design. Because you get a lot of forces at play on a transmission system. You're hanging these very heavy conductors at tension and stringing them, tens or even hundreds of miles between substations, and those are exposed to the elements and going to be having a lot of things that could happen with them. So some of the things that go into designing a transmission line is certainly the load capabilities. How much power do we need to go to transmit between one station and another, and depending on the needs of the project, is going to define what you'd use for different ratings. There's a lot of studies that go into planning where we need more transmission capacity based on loading and other equipment limitations and things like that. Once that's figured out, our transmission line engineering folks get in and start working out the physical parameters of how you're going to build the station. What kind of structures do you need? What does the spacing need to be? What tensions are needed on the conductors to get the appropriate amount of sag in the between the towers? What clearances do you have, and what kind of loading do you need to account for environmental conditions, wind, ice loading, things like that. You got to plan for these to be very robust. A couple of different kinds of conductors I've got over here. So the top one is a aluminum conductor, steel reinforced, or ACSR conductor. So you've got the aluminum strands are wound around the outside of the conductor, provide the primary path for your power transmission, and then you get some steel strands in the middle that provide strength for the cable itself to make the cable stronger. Another one that we see very often on new transmission lines is an optical ground wire. So I mentioned you'd have that ground conductor that would provide a path for ground fault currents and ground reference for the line. Generally, when those are put in these days, they're installed with fiber optics within the conductor to allow data transfer from one station to another, either for protection means or for SCADA systems. Could be used for other uses as well. They could rent out the fibers to a telecom company or something like that if they needed to, because they've already got the structures up there. Why not add some data capabilities as well? So, going a little further into transmission line construction and characteristics, we've got a bunch of different tower styles, and this isn't going to have a huge impact on our protection, but it is going to have an impact on the electrical response of the system, how we model the transmission line electrically, and potentially what the failure modes of the transmission line may be based on physically how they're connected to the towers. So you can see on here, we've got a few different tower structure types. We've got a vertical tower in the middle, kind of this H-frame structure here, and then a more of a steel lattice structure. But each of them have kind of a lot of the same stuff, where we've got these insulator stacks that are supported by the structure itself, either hanging or horizontally. And then we have some spots at the top where our ground wires would connect to those. So you'd have your 3 phases across the bottom, and then you'd have a static wire or ground wires up at the top that would be also part of that. Same thing here. You've got the 3 phases, and then you'd have something up top here that would be your ground wire. And this lattice tower here is a double circuit configuration. So you could actually hang off the other side of this another set of 3 conductors for a separate transmission path there. So you could have 2 parallel lines going between the same 2 substations, or you could just share this tower for part of your transmission right away for for a portion of that, and use this tower to kind of save on having to build another separate transmission structure to accommodate the other line. So that's the physical characteristics, but from a relaying perspective and as electrical engineers, we probably really care a lot more about the electrical characteristics. So how do we get from something like a transmission structure and a specification of a conductor to a electrical equivalent of the transmission line that we can use in modeling and in calculations that would inform how we set up our protection. So you may have gone over this in some of your other power classes, but basically the your transmission line, you can do a bunch of calculations to take the physical relationship between your conductors, the spacing between between your adjacent conductors and kind of each pair of conductors, the spacing between the conductors themselves and ground, how much the conductors sag, so halfway down the line, or between two structures, how low does that conductor go to ground, spacing between your conductors and the ground or static wire. They all play into your line impedance, and that's going to come in with your conductor impedance. So you're going to have obviously the conductor itself, that ACSR conductor for your phase conductors is going to have a resistance associated with it and an amount of inductance due to the kind of internal connections and relationship to each of the separate strands. But you're also going to have inductance between the conductors as well. So, the geometry of how your transmission structure is set up is going to have an impact on your model as well. And then you get capacitance. You get capacitance between your conductors and capacitance between your conductors and ground. So, if you actually look at the real detailed way of modeling this, the impedance of each conductor, even though they're following the same path, may not be equal, because you got unequal relationships between all of these inductance and capacitance, pairs on here. You can also have mutual coupling impacts. So if you had another transmission structure right next to this one, or you had one of those double circuit towers like I showed on the previous slide, you're going to have some flux linkages between the 2 transmission lines, so that if there's fault current or any current flowing on one, you'll have some impact on the impedance of the other one as well, and drive current flowing in that parallel path. So all this, you can do a whole lot of manual calculations on it, but luckily as practicing engineers, we got a lot of really great tools we can use to, basically draw out these types of relationships of the physical spacing and heights and things like that. And, that will output something that we can understand as the line model itself, and we can use that in our simulation programs. So we won't go into a lot on line modeling, but I did want to kind of make that link between the physical characteristics of a transmission line and the electrical characteristics. So once we do that and we take those physical characteristics and the ratings of the conductors and all of that other information, we generate what's called a pi equivalent model for the transmission line. So this would basically boil the entire length of the transmission line into a simple electrical model that we can use to estimate the parameters. And this is one of many approaches to modeling a transmission line. It's probably the simplest, other than just neglecting capacitance completely, which is, what we do for a lot of our analysis anyway. But basically, you can take the self-impedance of the transmission line and approximated self-impedance of the transmission line. That's going to be this, impedance here, resistance and inductance that represents the line. And then we'll model the capacitance effect between the conductors and ground as, and these would be distributed across the entirety of the line, but we kind of cut them in half and lump them on one side of the model or the other. So this is kind of the basic model that we would use in any of our modeling, and in one of the earlier classes going over Aspen one-liner as a fault simulating program. This is exactly how Aspen models transmission lines. And for most applications, other than a couple unique ones, we further simplify it and we completely ignore the shunt capacitive impact and only focus on the series impedance of the line. So we really try to simplify it as much as possible, because that line charging capacitance and the capacitive effects will have a minor, very small impact to the transmission fault response. So once we get that impedance model done, and again, we're ignoring the shunt capacitive effects, we can kind of simplify the entirety of the transmission system down to a simple model like this. And this is probably overly simplified compared to the actual analysis we do using a tool like Aspen one-liner, which would factor in transfer impedances and look further out into the system. But when you're looking at a line, basically you can boil it down to your transmission line is connected between these two buses based on the vertical positions here, and you've got a Thevenin equivalent source on either end. So you've got a sending and receiving end source, and in between that source you have your transmission line model, your impedance. So this ZL is just that resistor and inductor in series with this circuit. So if you kind of think about it as an electrical circuit, it is really fairly simple. It's just a couple sources with an impedance between them, and that's the type of analysis we can do for most of the most of the analysis we do on transmission lines. So this is where I wanted to get into some of that interactive piece. I wanted to keep things lively, make sure no one's falling asleep listening to me talk about transmission lines and relays. So I wanted to kind of hear from you guys. What do you think some causes of transmission line faults could be? I get a good picture here that might give an idea of potentially what a fault could look like. But any thoughts on potential causes for transmission system faults or transmission line faults?
Yeah, you need like squirrels in the line, right? Can't that cause a fault?
Yeah, animal contact would be a good one. It would have to, for a large transmission line, the spacing we're talking about in the transmission system, it would have to be a very large squirrel. So that's a bigger issue on distribution systems, but definitely animal contact would be a cause. Any others?
Like extreme weather.
Definitely. Yeah, extreme weather is a big one. If you have wind and ice, if you have a wind blowing intermittently, you can have these conductors actually swing. I mean, they're not static, stretched so tight they don't move. They can actually move, and you could have them, move and connect to each other, and that would cause a fault. Any other thoughts?
Vegetation?
Yeah, vegetation, that's a great one. So if a utility wasn't paying attention and a tree grew up here underneath, or if there's a tall enough tree on the outside of the transmission corridor that it could fall and make contact with the lines, it would definitely be a big concern. On transmission systems, generally utilities do a lot of work clearing the right of way. So if you have I have no idea why my slides are automatically moving forward, but here's the rest of the answers. But yeah, anyway, so if utilities do a lot of work to clear the right of way. So they will remove trees and keep track of vegetation growth throughout the transmission system. So they basically clear out wide enough that you're not going to have a tree fall on the transmission line. But in a storm or something, you could have a branch break and fall off and blow up into the line. Another big one is if you don't keep track of bushes and small trees getting up, even if it's not touching the transmission line, but it's getting close enough that it can arc over. That's another cause. But I think we covered a lot of the big ones. So, lightning is another one. These are big, covering hundreds of miles potentially, tall structures with ground on top of them. Lightning is very likely to hit these structures. Ice loading, fire could be another one. Smoke could cause a arc over things. Failed equipment, so insulator failures, or which might be the cause here. It looks like it's arcing between one of the insulators. Maybe that's just a jumper. It's hard to tell in the structure itself, or physical contact. How about different types of faults? What kind of faults could we expect to have to encounter as a protection engineer?
I can't get out.
Okay, just a second here.
Lightning, earthquake, and another disaster like a storm, wind, and so on.
Yeah, I'm sorry. Could you repeat that? My daughter's trying to cause a nuisance here. She's going down for my wife just got home. So I'm sorry.
Is it possible, the transmission line may be in future to be removed? Transferring power from a power plant to substation remotely?
Mm-hmm. So yeah, I think it's possible. There's a lot of work right now on microgrids and distributed generation and things like that could really reinvent how we look at power transmission. I don't think probably it'll go away in any of our lifetimes, but you never know. There's a lot of innovation going on. But largely, the utilities are in the process of trying to build more transmission to keep up with, growing demands from growing loads from electrification, data centers, things like that are a lot of the big things that utilities are contending with and trying to build more transmission. So, maybe someone here on the call can find future solution to those challenges. But the industry in general has had a huge amount of growth in the last 10 to 20 years just because of all the growth of that. So I don't know, maybe not anytime soon, but eventually I'm sure we'll find a way to not have to deal with some of this stuff. So a few of the types of faults we may run into are, we have three-phase conductors, so we can have a fault between all three phases from a single phase to ground, which would be what we have here. So, we got one of the phases arcing up to the grounded transmission structure. We can have a phase-to-phase fault, so again, if those conductors are, moving and make contact with each other or arc across, that could be another fault case. Or you can have something that, you have a phase to ground fault. So those are really the distinct types we're looking for. We, as protection engineers, we have to understand the differences between those and the types of schemes we would apply to protect against them. So if we break down the transmission system to this simple equivalent circuit here, we got a lot of additional complications that come with transmission lines that we wouldn't necessarily have from something like a bus or a transformer or a capacitor bank, some other system component. And probably the biggest one is that the transmission lines are huge. They're tens or hundreds of miles long in some cases. And that makes it so that you have to be able to react to a fault in any of those locations. So really the variable fault location has a big impact on fault response, because if we're looking from the perspective of the sending end Thevenin equivalent, a fault that's right close in on the beginning of part of the transmission line is going to have a much smaller portion of this impedance between the equivalent system equivalent and the fault location, compared to if the fault is all the way at this other line. You're basically having the full impedance between that location and the fault. So if you think about it from an equivalence circuit standpoint, if we put a three-phase fault here, you've got a voltage and you've got an impedance. If the fault's close in, your fault current is going to be just based on Vs and Zs. If you put it further down the line, it's going to be based on Vs, but then you're going to have a higher overall system impedance of Zs plus Zl. So as you move the fault location down the line, the amount of impact the line's own impedance is going to have on the system response is going to change. And in general, you're moving from a lower current or a higher current for a close-in fault and a lower current for a fault that's further away in the system. One of the other factors that we have is that the system configuration changes. So this is again a very simplified Thevenin equivalent here for the sending in voltage, but this would really be potentially 4 or 5 transmission lines coming off this bus, going out to other locations, going to multiple generators. That really makes the system up. And then we've simplified it to this source strength here, or the source impedance here. But what happens if you take a line out for maintenance, or you have a other system component, a transformer or something out for maintenance, or it's tripped off and it's already offline when your fault happens? Well, in general, that's going to impact this source strength. So as you take components out of the system, your source impedance is going to increase, and your fault currents are generally going to decrease. You also may have some generation dispatch changes. So, for instance, a nuclear power plant is going to go through a refueling every 18 months or so, where they shut down for a couple months at a time. Well, that's a large source on your system that's now offline for a known period of time, and your system response is going to change based on that. You can also have evolving faults. So you could have something like that last picture, that you start out with a single phase fault to ground through a transmission structure. And if it doesn't clear fast enough, the arc could arc over to one of the other phases. And you could turn from a single phase fault to a multi-phase fault. Let me go back here. And then you've got some other considerations as well. You've got transient versus permanent fault. So a transient fault would be something like a lightning strike that would hit the transmission line and then go away. So you trip the line off, but then you could close it back in, and there's no physical permanent damage to the line equipment itself. It just tripped off because of the lightning strike. Versus a permanent fault, which would be a failure of a component, a down conductor, something like that. So you can have a couple different fault types that we'd need to look at. So transmission line protection, because of all of these various things you have to consider, ends up being something we do a lot of analysis to make sure we get it right and cover all of these potential scenarios. So I got another opportunity for some interaction here. So any thoughts on what happens to the relay measurements, the voltages and currents when there's a fault?
It's all proportional to what the main line sees, right?
Yeah. So, if you put a fault here somewhere on this line, it's going to be dependent on where it is, but it's in general you're going to have an increase in current and a decrease in voltage because you've effectively for a three-phase to ground fault, you've basically grounded out this circuit midway down this line, and that's going to depress the voltage in the system. And it's also going to change the current from a normal power flow to a much higher magnitude because instead of being based on the overall system and the transfer of power from the sending to the receiving end over this line, it's going to be based on the strength of the system behind the relay location, which would be located at each end of the line. And I kind of touched on this one, the last one. What is system outages? What do taking a line out or other piece of equipment out do to your relay measurements? What your relay would see for the same fault that had a different source strength. And this is kind of a challenging one, but basically, as you take parts of your system out, it's going to impact your Thevenin equivalent here, this ZS primarily. And in general, when you take part of the system out, it's going to increase the source impedance because you're removing a parallel path. So as you're removing a parallel path, the overall equivalent circuit has a higher impedance to it. And that's going to decrease the type of magnitude of current that you would see there. And last one, how does fault location impact relay measurements? How's the location of the fault can impact what the relay sees at the terminal location here?
That just tie back into impedance as well?
Yeah.
Changing impedance exactly. To the distance? Yeah,
so the impedance between the equivalent voltage source and the fault location is going to change as you move the fault down the line. It's going to change on both sides because you're going to be feeding this fault potentially from both sides of your transmission line. So when you have a fault near this ZS terminal, you're going to have a very small amount of your ZL in between the fault and VS. So you're going to have a higher fault current there. And as you move down the line, that's going to lower. But it's going to be the opposite for VR, that for this first fault location here near the ZS terminal, the sending terminal, VR is going to see the full impedance of ZL between it and the voltage source. So, in general, faults close to the relay have higher currents and lower voltages, and then as you move further away into the system, that impact's gonna decrease. So, how do we evaluate faults to make sure they cover all cases? In general, the answer is we do a lot of analysis using tools like Aspen One-Liner. We go through and we simulate, dozens or hundreds potentially of fault cases and evaluate how the system responds, and then configure our protection with a focus on security, dependability, reliability, and other types of factors that we'll talk about later on to make sure that the protection is covering every one of those scenarios: close-in faults, far-away faults, the different fault types, evolving faults, different source strengths and outage considerations, mutual coupling effects. Kind of all of the stuff we've talked about so far is all stuff we have to understand as protection engineers and make sure that we are accounting for those in our protection. So I'm going to shift gears a little bit and talk a little bit about line protection, and we'll go into some of the specific schemes starting in the next class. But generally, your line relay is going to be located at the substation on either end of the line. So the transmission line itself, this tens or hundreds of miles long line, is going to terminate at 2 substations, and we're going to have our relays at either end that will use electrical parameters, so measured currents and voltages, to help them make a decision if the conditions they're seeing on the system are fault conditions or are normal operation conditions. So generally with this, we're talking about, with modern relay design, we're talking about microprocessor-based numerical relays that include, dozens of protection functions and schemes we can apply to, meet these protection objectives. And generally, we're kind of breaking that up and looking at a subset of those that are targeted to see specific types of faults. So generally, we'll provide different set of protection for ground faults, single phase to ground or 2 phase to ground faults, versus multi-phase or just phase faults, line to line or 3 phase faults, because the electrical parameters that we're going to be using are going to be different there. And each of those elements, we need to do some evaluation to determine their sensitivity and coordination and how those fit into the rest of the protection system to make sure that we're only isolating the line when there's a problem on the line, not when there's a problem on the adjacent bus or some other line off of that bus. So some of the key considerations in line protection, we've already talked about some of these, but I'll kind of go over, what we might want to think about when we're applying line protection. One is, the fault types and locations. We touched on that quite a bit. The line length, and that can be both a physical length or the electrical length. So, if you've got a physically very long line, there's some different considerations that you might have to take into place than if you've got a very short line. System contingencies, so this is the equipment outages, generation dispatch. You need to make sure you understand your line loading. How much load and power can this transmission line transmit? Is it built to transmit, so that you can make sure that the protection you apply doesn't trip it off under load. You may have tapped loads. You might have tapped substation or transformer part way down the line that you need to account for. You've got the mutual coupling effects of parallel lines. You've got accuracy considerations for current transformers and voltage transformers. And you also need to consider how fast does this protection need to operate. So the transmission system, oftentimes we're trying to get the total clearing for a normal fault clearing for a transmission line, well under a half a second, with many schemes applying redundant protection with the goal of getting it cleared within a handful of electrical cycles, be able to detect and make a reliable protection decision very quickly. And that's largely determined based on, you're protecting the equipment and also the critical clearing time of the system. So there's studies that happen that say, to dynamically protect the system and protect it from issues that can happen if you have long-standing faults, you need to clear the system in a certain amount of time. You also need to factor in what are your available communications for pilot schemes and other more advanced schemes, which we'll talk about in a couple days. And then the need for backup and redundant systems to cover the case where your relay fails or your breaker fails or other systems fail that play into the overall system protection. Because if you have a single component fail, you still really need your system to be able to clear that fault. Or it'll eventually clear on its own when it burns up enough equipment to do that. So I did want to touch just broadly, and I'm sure some of the other presenters have talked about these concepts throughout the classes here. But generally, when you're discussing any protection system, the best way you can describe it is with these protection system objectives. When we evaluate the adequacy of a protection scheme, these are the things as protection engineers that we should be framing that discussion and that evaluation on. So the first one's reliability, which is the assurance that the protection scheme will operate correctly. So, that's a big one. We want to make sure our protection scheme is doing what it's intended to do. But reliability is kind of broken into two components. There's dependability and security. So dependability is the degree of certainty that a relay or system of relays will operate correctly. So it's when there's a fault on the line, the relay will detect that and will issue a trip command to isolate the problem. The flip side of that is security, which is the degree of certainty that the relay or relay system will not operate incorrectly. Now, at first glance, you might think those are kind of the same thing, but security is more focused on if there's a fault somewhere else in the system, or if there's a non-fault load condition, or some other scenario that is not a fault that this relay was designed to operate for, should operate for, that the relay doesn't operate for that case. So you can, balance these out, and based on however you apply your scheme, that ideally you find the right balance between just dependability and security, and those two put together turn into your overall reliability of the scheme. Because you not only want the protection to trip for faults on your line, you also don't want it to trip for faults in other parts of the system, or you don't want it to trip under load. So an aspect of that is selectivity, which is the goal of maximizing continuity of service with minimum disconnections. So this is basically that case for if there's a fault on an adjacent line or another part of the system, you don't want the relay associated with your line to trip for that fault right away. You want to give the line relays or the other protection for that other system component an opportunity to trip first. And that is the goal with that, is to make it so that when you have a fault, you remove the smallest portion of the system as possible. So if you have a fault on a transmission line, ideally you're clearing just that transmission line from the system, and then everything else can remain in service to keep the overall system integrity as high as possible. Speed. So obviously it's in our best interest to clear electrical fault to the power system as fast as we can. But that comes with trade-offs, because the faster you make a decision, the less likely, or the more likely you're going to make a bad decision. Maybe it's you make a decision too fast and you trip off for that adjacent line. So as much as the goal is to make things as fast as possible, we also have to do that with reliability, the security and dependability criteria in mind. And in general, for transmission lines, we've got a lot of different schemes that we can apply, especially once we start getting into communication assisted schemes that provide that balance. You can have a transmission line protection scheme that can detect and trip a line off anywhere on the line with any fault type in just a few electrical cycles or even less. But you need a lot of logic in there to accommodate that. You need communications and other things. And that brings us into the next thing, simplicity. So, oftentimes the more reliable and the more high speed and selective you want your scheme, the more complex it gets. But there's a lot to be said for designing with simplicity in mind. The simpler solution is generally going to be your better solution, and you're going to, as long as it meets your protection objectives. If you start, reinventing some Rube Goldberg logic protection scheme, it's going to be really hard for people to maintain. It's going to be really hard for future engineers to understand it. And there's a high likelihood it's going to cause problems at some point, because the more complex it is, the harder it is to cover those kind of fringe edge cases. And lastly, economics. You want to provide the most protection you can at the lowest cost. Relays and protection is a very small piece of the overall cost of operating the power system and substation upgrades. So generally, utilities don't avoid providing the right protection based on cost. However, there are some cases that does come in. If you needed, for instance, your scheme needs fiber optics between two substations that are 100 miles away, economics comes into play really big on that, because running 100 miles of fiber optic cable is going to be a, astronomical expense. So, maybe the economics would start coming in there that there's, we might start looking into other solutions. So I'm going to use the rest of the class to just talk a little bit about some of the protection element types. But before I do, any questions or anything on the stuff I've been talking about for the last little bit, specifically about these protection system objectives? And these can be applied to any protection, not just transmission line protection. But any questions on this stuff before we move on? All right. Well, hearing none, I will continue on, and move into talking about some of the typical protection schemes and protection elements. So first one I'm going to talk about is distance protection. It's probably the most common type of protection for transmission lines. And it can be broken down in kind of two categories. There's phase distance protection and ground distance protection. Phase distance operates for generally operates for faults that are phase faults, so three-phase faults, phase-to-phase faults, and somewhat for phase-to-phase to ground faults. It operates, it's probably a little bit of a misnomer, but you set it based on impedance. So you've got that the line impedance itself. And as I mentioned, as you move the fault down the line, the impedance between the terminal and the fault changes based on a proportion of the line impedance. So you set distance elements based on the line impedance. And it might be something like you're going to set one of your elements to look 80% of the way down the transmission line impedance, and that would be the reach of how far it would look. To apply a distance scheme, you're going to need both currents and voltages for this scheme, because you're going to need to take those measured quantities and turn them into a apparent impedance seen by the relay. And this type of protection is going to be used in a bunch of different schemes. So step distance scheme, which I think is what we'll talk about on Thursday, and then also in permissive and blocking type pilot schemes, which we'll talk about next week. Couple other things with distance protection. It's directional. We generally provide multiple zones of protection. So you wouldn't just provide one element, you might provide 2, 3, some schemes you might provide 4 or 5 separate elements that are set in a specific way to look a certain amount distance into the system, have different timers and delays associated with them, or used in different schemes. And you're generally setting them, because they're directional, you need to set them is either forward-looking or reverse-looking. So forward-looking means it operates for a fault on the line. Reverse-looking means it would look behind at you for faults in the system behind you. So generally, there's some mix of all of that stuff applied, and we'll talk about some of these schemes over the next few classes. Ground distance is very similar, except it uses zero sequence components quantities. And it operates for faults involving ground, so single line to ground or phase to ground faults. But it would be very similar in all the other aspects of the types of stuff that we talked about for phase distance. So a few of the other types of schemes we typically see is directional ground overcurrent. So this is an overcurrent protection you probably talked about in some of your other the other classes, is operating on current magnitude, basically. And then there's a bunch of different types of schemes for instantaneous or time-delayed elements, things like that. But generally, we're providing kind of a forward directional looking ground overcurrent element. It's going to operate on zero sequence current, so it's just going to respond to ground faults. And generally, we're going to need both line current or line voltage or some other polarizing quantity, which is what we're going to use, because we're going to need not only the current magnitude, but we're going to need to know its angular relationship to some reference, so we can tell, the direction of the current. Is it flowing into the line, or is it flowing out of the line in respects to the terminal? Directional ground overcurrents used in some permissive and blocking pilot schemes, but generally is also used as a direct tripping element. So if your ground overcurrent element asserts, indicating there's a fault, it will trip the breakers and clear the line. Switch on to fault protection is another type of scheme we apply. This is generally designed to protect against a scenario where they've taken a line out of service. When they do that, they ground out the line conductor. So the personnel that are working on the line, the linemen up there doing the maintenance, the transmission structures or whatever needs to happen, can guarantee they're in a de-energized state. This protection covers the very unique case that somebody forgot to take those grounds off before they closed the line in. So because the grounds are right at the terminal, you would never be able to generate any voltage or your voltage transformers. So the schemes we've already talked about all rely on voltage as an element, so can defeat your protection overall. So switch on default is just enabled briefly at after a line is energized. And it covers that very specific case where you've left your grounds on the transmission line terminal. Someone closes it in because you need a way to clear that fault case. And then lastly, we'll talk about this next week, is line differential protection. So line differential protection is something that's not new, but it's been much more widely applied in the last 10 years or so as the technologies come along. And this protection uses a differential principle. So basically the current into and out of the transmission line measured at each of the terminals has to equal 0, or else there's some problem that has provided another path for that fault current to flow. So this type of scheme uses a communications channel to share current measurements from each of the terminals to calculate a differential current, basically sum the currents into each terminal and determine if there's a fault. So required inputs are just line current in this case, but you need line current from every terminal. So, and you need a good robust communications path between there to share the data in a high reliability, high speed fashion so that we can use that data accurately. And we'll talk a little bit more about that scheme in a few days. So as kind of a wrap up to things, today we talked about, transmission lines as part of the power system, physical characteristic, electrical characteristic, fault considerations, causes of transmission faults, the types of faults, how does the system respond to faults? And we covered a little bit on some protection basics of the protection system objectives and some of the elements we'll be talking about over the next few days. So just to kind of look ahead here, we did the overview today. We're going to be doing a deeper dive into distance protection and step distance schemes on Thursday. And then next week, we're going to cover pilot protection and then the line differential protection and kind of a wrap up summary of some of the stuff that we've talked about. And with that, I think we can probably wrap up, but I'll open it up if there's any kind of questions or comments or feedback or anything.
Where can we find the formula for line protection and any other formula for other aspect? I mean, the fault protection, line protection, and the formula for ZL, ZS, and ZR.
Yeah, so they come from a lot of different sources. A lot of what we use as practicing engineers is different modeling software. So to come up with that line impedance parameter, the actual ZL, it's going to be we'll use a piece of software like I think Aspen has Aspen line constants or line database software that you model the physical characteristics of the spacing and things like that. And it uses math behind the scenes to then output the impedance per unit length. If you want to do it by hand, I've done it before. It's definitely possible. But I'd refer to, I think, probably a lot of just general power system analysis textbooks would have that type of thing. As far as the general references for finding out more about any of these protection schemes and applications and things like that, I assume UMaine has access to IEEE standards, but any of the IEEE guides are all really great references, and they're intended for kind of early career engineers who are trying to learn about more details about specific protection topics. So it's generally the IEEE C37 standard series, but they have guides for everything. They've got a guide for transmission line protection. They've got a guide for line differential protection, guide for bus protection, transformer protection, capacitor bag protection, and they're all really great places to look for that information.
Thank you.
Yeah. All right. Any other questions?
Yeah, looking forward to the line protection on Thursday. Would you say, you definitely have different zones of protection. So with the line zone of protection, you have a few different protection elements watching the line. Would you say line differential is, a protection element that's kind of been developing in these recent years that will be better than your impedance-based line protection? Or I guess if you were to prioritize one over the other, how would you rank them?
Yeah, I think I'll touch on that in one of the probably the day four of the line protection stuff. I've got a table that I kind of put together that kind of compares and contrasts them. So nothing is a one size fits all. Everything has considerations that go into it. For most lines, if you have the ability to do line differential, it's probably a really good idea. It's got the benefit of being a very defined zone. It's differential, so you've got current into and out of defined points in the system, and it'll operate for any fault in between them. But it's got like the selectivity and security aspect of it is very good. Yes. The complexity side is the other, and like all those protection objectives, you can't really push one without having an impact on the other. So it's a much more complex scheme. It relies on a more robust communications path. It might be more susceptible to communication channel issues, problems within the channel itself, drop packets and things like that. But there's a lot of really smart stuff in the relay to compensate for a lot of that. But generally, we see a lot of utilities doing a mix. If they got to apply two schemes, they might do line differential on one scheme and then do a redundant system with an impedance-based pilot scheme. But we'll touch on both of those a little bit later. But yeah, I think there's probably not a one-size-fits-all is the best approach always solution for anything. But in most cases, if you've got the communications infrastructure already there and available, line differential is a pretty promising place. It's probably the closest we'd get to the one size fits all is a good solution, because and you think about it, it's just get more data about the system. Every other scheme's relying on a very small amount of information, the local terminal plus a very small amount of information about what's going on at the other terminals for the other communication-based schemes. But line differential actually has direct measurements throughout the system. So,
right, as long as you have the money, the modernization, right? Needing Goose or pretty fast pilot scheme, something.
Yeah,
that seems.
Yeah, and a lot of utilities have been over the last 10, 15, 20 years, whenever they do any transmission work, they add fiber. And that has helped a lot for the utilities who had enough foresight to invest in that, because now they've got a very robust communications network to pull from for, applying these schemes. So.
Awesome. Thank you.
Great. Well, we're just about at time here. So I'll see y'all back here on Thursday. Really excited to see we got so many people interested in moving into this industry. I think it's a really, great place to be, great, career growth, a lot of interesting stuff going on, really big ability to make a good impact on, the future as we're doing more and more electrically with electric cars and renewables and data centers and all this other electrification that's going on everywhere. We need a lot more people moving into the industry. So it's exciting to see folks who are already in the process of getting there. So. All right. Well, thanks everybody, and I will wrap it up here, and we can talk again on Thursday. But if you think of some other questions, just bring them on Thursday, and we'll open up with roundtable. Anything else you want to talk about? So, all right. Thanks everybody.
Thank you.
Thanks, Brian.
Thank
Thanks.
you.